So, my name is Witold. I run a small team of embedded security engineers back in Wrocław, Poland. Basically we do all the low-level hacking, including hardware security recently. So the topic of this talk is use of side channels in continuous integration, because, well, these days pretty much everything is CI/CD pipelines, and if you don't do security, you basically can't deploy. So you have to do side channels in continuous integration pipelines these days. The story actually is the story of the cloud that we build is basically COVID story. So back in 2020, we had a hardware security project going on, and because of the lockdowns, we lost access to our lab for months. Couldn't work, so all of this equipment back there, and we can't do anything. So we figured we need this online like yesterday. And basically, a couple months later, we built a remote access into all of this equipment and around all of this equipment. And after we did that, we figured, well, now that it's online, we could give other people access as well. And after we did that, we figured we can do some quality of life improvements. So webhooks, GitHub integration, and we can basically run regressions on this system. So that's the story. Took us quite a while to get there, but it's now pretty stable, and there will be live demos also. So we'll break advanced encryption standards today in 2 minutes or less, and we will also run side channel regressions at the end of the presentation. So, intro, we're here. Why we should do side channels, and why should we do side channels in CI? And then how. In a process, so how do you build a development process with side channels integrated? What software do we use? What hardware do we use? And, of course, live demo after. So why do side channels? Well, side channels, people think side channels, what are side channels first? So these are physical effects of computation. If you compute anything on a physical chip, of course, it has physical effects. So computation takes time, computation takes power, and also it produces garbage and in terms of audio, heat, and electromagnetic radiation. Of these, for our side channels, actually the first three are most useful, because audio and heat is not much resolution there. So not much frequency, not much resolution to produce. There are practical audio attacks, but they are rare, very rare compared to the other three. So why do side channels? Well, people think side channels are hard, and it's true to a point. I mean, there's a steep learning curve. Initially, you operate at a much lower level than people normally think low level is. And there's some heavy math involved initially. But once you get there, actually, the attacks are remarkably portable between different chips, between different encryption libraries, for example. Their awareness is also very low. So not many people worry about side channel countermeasures in their code and their libraries. So basically, it's open season, right? Once you can do it everywhere. They are also hard to secure against, hard to test, and basically hard to do countermeasures unless you have secure hardware already. So if you use a secure element like an NXP chip, for example, with side channel protection internally, that's better. If you don't have a secure element, it's very hard to protect against side channels. And the market is very concentrated. So for IoT and embedded, pretty much everyone uses ARM these days. So there's like a couple chips that cover like 90% of the market. And for software, it's even worse, because for years, decades even, we've been telling people as security professionals never to roll their own crypto. So everyone uses the same library pretty much, or the same implementation. There are actually three. that we attacked. So we attack Embed TLS, Tiny IES, or Wolf SSL, and this is pretty much everything that's out there. There are of course some people that still roll their own crypto, but even then, from a theoretical point of view, there are like 3 major ways you can implement AES. So even if they roll their own crypto, it's pretty much the same implementation as the other 3 anyway. So this is the first demo. So I will go here for a moment. So this is running on our mothership. And let's just run this. So this is a correlation power attack against advanced encryption standard in Embed TLS on STM32F3. This is a software implementation, software encryption. And we use, for the purpose of presentation, we use chip whisperers. So if you have a chip whisperer, you can replicate this. All of our attacks that I present here are public. And some of the attacks that are not public will be public anyway, because we operate under a grant from Polish government to do some research. So everything we do will be published eventually. So we're just flashing the target with firmware containing the Embed TLS library. And we will be attacking the first round of AES. We will collect 500. So this is an example power trace. This is how AES looks in power on this particular chip. And this is how long it takes to calculate. Okay, I'll try. Let me. I should be able to hide this also. View, yeah. So now we will collect traces. So this is 500 traces. As you can see, it takes 6 seconds to collect 500 traces. What we actually need is about 200, a little less than 200, but the presentation, this demo is designed to absolutely never fail. So it's way overkill. Yeah. And after that, there's a little bit of analysis. So I don't know whether it shows, it does show on the projector. So these tiny differences in power that you can see here, for example, or here, this is what we will be using to recover the encryption key. So basically, depending on what the key value is on a particular moment in time, the power the chip consumes will vary. So we test with different inputs with the same key, and we basically guess 1 byte of the key at a time. And if we just sort the guesses, oh, that didn't work actually. Hold on. Let me do that again. Yes, something broke. Okay. I'll just. Okay. Sorry for that. I'll post a video. I post a video after that. I don't know really what happened. I tested this like yesterday night on the hotel room. Okay. Let me go back to the presentation. Sorry about that. So anyway, there's a screenshot here where we do recover the encryption key after 500 traces. So yeah, that's how it's supposed to look. And down there, we have a better attack that actually recovers the key in 20 to 40 traces, depending on the chip. But what's remarkable, what's nice about this particular attack, is that this exact same notebook works across every STM32 that we tested, and across all three implementations of AES. So Mbed TLS, Tiny IES, and Wolf SSL all fall to the same exact notebook. No changes in code, same exact thing. So that's why I think side channels are actually easier than most people think. Once you get it, and once you get it working once, it works pretty much every time. So if I get a new sample or a new chip, I don't have to invent a crazy buffer overflow every time someone rolls a new software. I can just read the key out of the power trace, and it's every time the same power trace, the same method, really. So here's how the state of IoT hardware security looks. Mostly it's non-secure elements, because secure elements are expensive, so most of the projects don't deploy secure elements. And most of the chips are low clock, so a couple megahertz maybe, maybe not even that. And customers have physical access to them. Obviously, because that's IoT, you sell these devices, you deploy them in the world. Some of them are sensors that are outside of buildings that even other people, not just the customer, but other people also have access to. So you have a non-secure element, so a chip that was never designed to be exposed to attackers physically, and they are physically exposed to attackers. And then they use off-the-shelf encryption, obviously, either hardware or software encryption, but still it's mostly off-the-shelf. So we have 3 notebooks deployed currently. The one that you saw is for software AES. We also have one for hardware AES, and this breaks STM32F2 and F4 hardware AES, also same exact notebook. It does require a better scope than Chip Whisperer can provide, but other than that, not hard. It's just, more expensive, a little bit more expensive, but not much. But the cost of attack estimated on a typical IoT devices deployed like that is about $100. So you pick up a Picoscope off of eBay for $80 and you have a laptop. So threat level, clever teenager with their lunch money, right? Pretty much that's the state of hardware security IoT. So I think it's a very low hanging fruit once you get the initial knowledge to get through the low level stuff and the math. It's quite low hanging fruit currently. It's way cheaper than finding than looking for buffer overflows or trying to dump and decrypt firmware, for example. So why do side channels in CI? Well, also it's easier than you think. And really, there's no choice. Like I said on the first slide, software is done in CI/CD. Once you have a hardware prototype, you will iterate software. So if you don't do side channel, you have 2 choices basically. Either don't do side channels and then you're vulnerable, or don't do CI, right? Don't stick to a traditional water flow process, which kind of sucks if you're not in, like DevOps, CI/CD process. God help you these days. So traditional cycle, DevOps, maybe security later. So people, the CI/CD DevOps approach is often used currently, but security is rarely integrated. Usually it's like 9 months of DevOps and then security at the end of it. And of course, when security says nope, then you do all the entire process again. If it's a big vulnerability, like if you need to change hardware, for example, then it's like 12 months the delay, right, in the project. Also, the vulnerabilities are exposed late in the cycle, so they are expensive to fix. The dev team has no feedback for months and has no clue how to do secure coding because of that. And you have no automation, so each iteration is slow. So modern approach is DevSecOps, and if you Google for that, there are these cute two pictures, and it's obvious from these two that nobody knows how to actually do it, because and the first one on this one on the left, the security team does everything. It is integrated, but it's not. You don't know what the security does, and then the second one, of course, there are things that security you know what the security team does, but it's not integrated. It's just separate processes, right? So today we'll try to answer how to actually integrate it and answer what security team would actually do in this process. And of course, the goal is to discover vulnerabilities as early as possible, have quick feedback, and have automation. So the process that we're using is test-driven CI/CD. So we write tests first. This is nice because we know what AES looks like, right, every time, and pretty much you never change crypto, right? So you can write tests in advance. Once you settle on crypto, on which encryption algorithm you're using, you can test it in advance. The difference between a regular TTD, test-driven development, and our TTD is that our tests succeed initially. And the reason is, if you don't have code, it doesn't leak information, right? Once you start implementing stuff, the tests will start failing, and then you have to go back and fix them. But initially, so the common complaint about this process is that people think security doesn't have to, so you have no application initially, so security has nothing to do because there's nothing to analyze. Well, actually, that's the best time to select targets, for example. So even on non-secure elements, there are chips that are remarkably resistant to some attacks. We don't really know why, but they are. So you can try to test that in advance. You can, of course, set up the side channel hardware. You can try to look for fault injection parameters and fault injection setups. So for us, for example, the glitch search for glitch parameters takes a couple days sometimes, just the search, automated search also. Because the reason what you need is a glitch that doesn't crash the chip, but does something interesting. So you do a very wide and very fine-grained scan across power, across voltages, clocks, and so on. So it's a very, 20 parameters maybe, and very fine-grained search. And of course, you should, at this point, you should also set up instrumentation tools, so debuggers, for example. If you want, like chip whisperer approach, you can use one pin to inform the oscilloscope when to fire. That's also useful instrumentation that makes the tests much easier later on. If you don't do that, you have to align traces, which takes a long time, a lot of computation. And during the process, so during the standard DevOps cycle, the SEC team, of course, does vulnerability analysis, and attack and test specification and automation countermeasures, but only for the hard stuff, the stuff that's new, the stuff that's just been discovered. The day-to-day vulnerabilities should be covered by the regression tests. So your development team would do that instead. And that's new in this process. Normally, development team just develops features and fixes functional bugs, perhaps performance bugs, but not security. Here, development team also does security, and that's great because there are many more developers than security experts, and also they learn. They do security, so they learn. They will become security experts eventually. And I started as a developer, and I worked in a waterfall initially, and I got feedback from security team after 9 months of projects, and I had no idea what to do with it. So there were long discussions on how to fix our application, even after we got feedback from the security team. So I know from experience how the traditional process doesn't work. So there's a big difference actually between attacks, secure side channel attacks, and side channel tests. For attacks, you go depth first, so you pick one vulnerability and you dig deep. The idea is to get exploit out of it, and then standard waterflow, the standard traditional process. You only fix the vulnerabilities that are actually exploitable, because you can't fix all of them. It's way too late. And the attacks are instance specific, so all the way down to specific stack layouts, specific values of pointers. You know the drill. The exploits are very instance specific. If you roll a new version, it may not work. It's not portable. For tests, we can't do that because the application is not finished yet. We know it's going to change. We know it's going to change fast. It will change daily, maybe weekly, but still, you can't do a depth first approach. You need to go broad. So your attacks will be general and adaptive. So for example, look at the power trace and figure out as much as you can from the power trace alone without the knowledge of the application, without knowledge of the actual code underneath. We don't have a need for a full exploit because we're early in the process. It's easy and cheap to fix all the vulnerabilities. So we don't go for exploits. And we will use instrumentation and debuggers. So for attacks, if you say, yeah, I found this awesome exploit, but it requires you to physically connect a debugger to the chip, people will not like it, right? For tests, this is necessary because you need this process to be fast. So, and actually, it's quite easy to model how much harder an actual attack would be once you have a debugger and a test with a debugger and instrumentation. So it's quite easy to predict how resistant the final application will be without instrumentation when you have this setup with instrumentation. And the goal is to find what information, so you define your secrets, could be a key, could be some other information, some other data. But the goal here is to figure out what leaks, not what's exploitable, but what leaks, what information gets out of the chip in this side channel, in the side channels. And of course, if you don't have an exploit, it's still a problem in CI/CD because application is not finished, so you still don't know whether it will be exploitable, and you need to fix it anyway. So our software, top level, top down, is we use a CI/CD on GitHub or GitLab. We operate on GitLab actually, but GitHub is more popular, so we have bindings also for GitHub. So we have custom actions for resource management. So basically, we have what you get on. We were a public cloud, so you can just try it yourself. But what we do is we launch a virtual machine for you. So you have a custom action to start a VM with side channel hardware and software. Then you have on this VM you have a tagged self-hosted runner for execution of the actual test, and then at the end of the pipeline you have a shutdown. So we're a public cloud. I will show the GitHub CI also at the end. But if you're not a public cloud, you want to keep this in-house completely, then still you can do custom actions. But you would also use run the custom actions on your self-hosted runners within your private network. So that's also an option. You can do this self-hosted. You don't have to expose the lab to the world. For hosts, we use Linux, KVM, libvirt, and we extensively use PCI Express pass-through for GPUs, for USB controllers. And I will touch on the PCI Express later. So here's our minimal CI setup. This is a little bit hard to read, maybe, but there's a start job here that runs on Ubuntu latest, so basically runs on GitHub itself. Then there's a tagged run SCCI job that runs on a custom runner, and then there's a stop job. So what hardware do you need to run side channels? Well, you need power measurements normally, so you would use an oscilloscope or a data acquisition card. The difference is that oscilloscopes usually for dollar oscilloscope will be cheaper, but it will have terrible I/O. I will also show that. Data acquisition cards are more expensive, but they have great PCI Express level input-output, so a couple gigabytes per second you can pull out of that. The problem with data acquisition cards is they don't pass through nicely. At least we didn't find one that does yet. So they are not stable in PCI pass-through, at least the ones that we tested. You need a trigger, so that would be a logic protocol analyzer, could be a debugger, could be an FPGA. Also, Chip Whisperer has all of these integrated, of course. And then you need a target, so a dev board or a prototype. Once you have that, you can start iterating software. And then you need fault injection hardware. Honestly, I don't have a great answer for that one because we're still working on this. A hardware debugger like a Lauterbach, for example, is good here. But for power, for example, you need custom hardware pretty much. So Chip Whisperer has glitching also, and the clock glitching is useful, but the power glitching isn't. So for power glitching, for power attacks, we are rolling our own PCB. Basically, what Chip Whisperer does is they short VCC to ground for a very short period of time, which is too aggressive most of the time. And what you want actually is to lower the voltage, hold it there for a defined period of time, and then go back up. And you need to do this gently. Otherwise you crash the chip. And on top of all that, you need to be able to shut down power, because especially with glitching, your stuff will just crash sometimes. And I don't mean just the device under test. Sometimes the oscilloscope will crash also, even in the high end. We've seen that. So you basically need to restart it once in a while. Thankfully, all of this is covered pretty much by PCI Express pass-through. Basically, debuggers, FPGAs, oscilloscopes, all of that runs on USB. So you pass through an USB controller, and the VM has native access to the hardware. For power toggle, USB standard has hubs. USB hubs have what's called PPPS per port power switching. So you can toggle USB power on and off within a USB hub. Problem is, the vendors for USB hubs don't solder on the actual MOSFET that does this because it costs money. So the controller, the chip that does USB supports PPPS, but the hardware is not capable of that physically. You can solder that on yourself, or you can just keep looking for hardware that does have the MOSFET. So you'll need hardware that's capable of virtualization. So IOMMU is absolutely necessary for pass-through. If you read online, some articles will say that you need function level reset devices to be able to pass through. That's not true, actually. It makes them more stable, but it's not necessary. And here's a Fresco controller that we use that doesn't have the FLR capability, but it's actually the most stable controller that we have currently. And for USB PPPS, there's a great GitHub repository with a list of USB hubs that support it. Basically, you need to test a couple, and then once you find one that works, we just bought like 20. And even then, if you have all the capabilities, so IOMMU and FLR, some things just won't work. And we tested multiple motherboards, multiple devices with, for example, our data acquisition card has FLR. And there is one motherboard where it will never pass through. There is another motherboard where it will pass through like half the time, and the other half, it will just crash the host completely, like not even a panic, just dead. So you have to, there's quite a lot of try and fail to that. And that's how it looks in practice. So there's a little house of cards out of motherboards. These are all failures. And these are controllers and hubs. Hubs are actually working. These are functional. The controllers aren't stable. They work in pass-through, but they aren't stable. So then there is a question of hardware multiplexing, because in CI you will have multiple branches, multiple repositories. You'll do releases quite frequently for different hardware targets maybe. So you need to multiplex your expensive hardware between different targets, or in our case, between customers even. So generally, digital is easy, but what do you do about the analog side? Because you have this expensive scope. It has the BNC connector, and you need to multiplex that between different targets, right? So basically you do an electromechanical switch, programmable electromechanical switch. You lose a little bit of bandwidth on that, but it's quite manageable. These on the left, on the right are what you would normally, what you wouldn't normally buy because they are crazy expensive. So we basically soldered our own, as usual. So the one in the middle is what we soldered. It's a 2-to-1 SMA switch, electromechanical, and that costs like $3 maybe. And the others on the side are a couple thousand, by the way. So here's a little quiz. So this is a loop. Basically, it's a simple password check. And this code is not constant time, but it's not obvious why. So have a look at that for a moment. So obviously, we execute the same number of iteration every time because we iterate over the size of secret, which is constant, but it's still not constant time. And the point is that, depending on the type of the OK variable, it's either constant time or not. So on ARM chips, you have a conditional move. So if the variable is 32-bit or shorter, then it's one instruction, conditional move. But if it's 64-bit, it's actually 2 load stores. And it can no longer be a conditional move. It's just a branch. And it takes longer. This if this store, this OK store, within the loop is not constant time. And this is a bug that is actually a distilled version of something that we've seen in production. Basically, there was a variable with a 32-bit native integer type that was later changed to 64-bit. And there was a timing vulnerability because of that. And it passed review and passed, It's a single it's a single line of code change in a big project somewhere deep in the header. You'll never see that. It never shows up in review. So here's how. Here's why specifically. So if it's a 32-bit, then there's this conditional move, and if it's a 64-bit, then there's a branch in there, and it's not constant. All right, so let's go to the demo. I actually have to stop all of those. So a little bit about the example. It's a simple password check like before. I'll just show this. So it's basically the same code that we've seen on the slide. And it's either 64-bit or 32-bit here. So let's commit something. Let's edit that. And then we can look at the actions. So if you look at the build and test, at the end of it, you have a test passed, test failed, and we have two tests here. First, where we use the power trace, and we just detect the timing vulnerability based only on the power trace. We don't measure clock cycles. That's a more realistic scenario. On, for example, a smart card, you don't have a clock that you can measure really. So power trace is the only thing you have. But also we have a test without power trace, so we're just calculating cycles. And then let's go back and make the vulnerability, and hopefully that one works. So yeah, the password was very safe, of course, and the tests failed, both of them. And also the test case has a full attack included, so we do actually recover the entire key. For the purpose of regression testing, this is not necessary, but I did that just for show. So yeah, that's how you run regressions, side channel regressions, basically. And a bonus at the end. Let me just go back there. So, like I said, benchtop scopes have terrible I/O. So we have this big Tektronix that can't even saturate a gigabit connection. So basically, we speeded up our trace gathering 4 times by soldering on a couple of MOSFETs to a $10 USB switch, and we switch an SSD, a USB 3.0 SSD between the scope and the PC that's controlling the scope. So we save the traces on the SSD instead of the onboard storage that the scope has, and then we download them, switch the SSD to the PC, and we copy the traces out. And this is 4 times faster than the native I/O of the scope. And it's pretty much true about any benchtop scope. So that's a bonus. I think that's our time, actually. Any questions?
Any question, guys?
Yeah, thanks for the talk. In the beginning, you had an example of attacking AES, and where you said you only need between 20 and 30 traces. Can you explain in more detail what exact side channel you were attacking there and under what conditions?
So we were using correlation power attack, but with learning. So the 500 traces that you saw, or didn't see because it didn't work, but the 500 traces uses no machine learning whatsoever. It's a dumb attack. But the one with 20 power traces learns from the power trace and selects very precisely where we measure power. So it's an adaptive attack, and that's why it takes way less traces.
But not known ciphertext or known?
No. It's basically, we don't know anything about the key, or we just run encryption. That's it.
Okay, thanks.
Anyone else?
Yeah, hey, hi. So my question is about some prevention techniques, as you mentioned. So can you just explain one of that? Like, let's take this instance. You worked over the power tracing, like tracing powers. So how we can prevent these, like tracing? Like, do we obfuscate these things, like producing random signals and all?
Okay, so there are a couple. So basically, let me backtrack a little bit. So if you don't have a secure element, basically the simple answer is you can't. I mean, you're not protecting. You will never protect against like government or an organization level threat. But even on a non-secure element, you can protect against a chip whisperer level threat. That's the answer for whether you can secure it. But how you can secure it, there are techniques. So, for example, we have an implementation of AES that only uses the lower half word, and the higher half word is filled with the negation of the lower half word. So when it leaks power, basically the Hamming distance is always the same. So it masks the power, the higher half word masks the power of the lower half word. This is also half true because if you have a high enough sampling rate, then the lower half word is calculated a little bit earlier than the higher half word, so you can still pick it up, but it's way harder. You need a bigger scope for that.
Thank you.
It's an example also. There are quite many techniques that you could use for masking. What we found works great is basically changing frequency of the chip every iteration, for example, to as some disturbance to the frequency, because what it does is it breaks trace alignment. So you have the power trace. Normally you have all the power traces aligned, and one of the points in this power trace will contain the information about the secret. If you change the frequency each iteration, you're basically losing the alignment. So there are techniques to undo that analytically from the power trace, but it's also way harder to do than your normal chip whisperer level analysis.
We have another question over here.
Hi. Is it on? I don't know. I'd have just the idea, like, would it possibly be an idea to use something like homomorphic encryption while encrypting, so to mask or obfuscate the process of the encryption by previously using some homomorphic encryption to have the end result really encrypted in a different way? Like,
yes. So basically, there are masked AES implementations that do that. They are much slower, like order of magnitude slower.
Obviously, yes.
Obviously, but yes, it's possible to do that. There are also power attacks, so it's called higher order power analysis, which can also break that. But again, it's way harder than, yeah.
Thank you.
Thank you.